Okay. Now, the last time what we said about was that optical rotation, which is a very important physical parameter for optically active compounds. Okay. And this is useful not only to measure that to identify one compound with another compound, and also to measure the percentage excess of one enantiomer over the other. So, we have introduced the concept of enantiomeric excess, or and also what is also known as optical purity. Okay. Now, before I go further, let me again clarify some of the terminologies that are used in stereochemistry. We have been exposed to at least 2 or 3 of these, but again just repeat these. Enantiomers, what are enantiomers? They are non-superimposable stereoisomers, which are non-superimposable mirror images of each other. Okay. They are chiral in nature. Diastereomer, they are stereoisomers, but they are not mirror images of each other. Now, what about the chirality of diastereomers? They may be chiral or they may be achiral, both. Okay. Racemic mixture, it is a 50-50 mixture of the two enantiomers. Okay. 50-50 mixture or 1:1 mixture of the enantiomers, of the pair of enantiomers. So, the rotation of racemic mixture will be 0, plus or minus 0, because the plus compound is present in equal amount. So, it will try to rotate the plane of polarized light to x degree, plus x degree. The minus compound will offset it by turning it back to minus x degree. So, the total rotation is ultimately becomes 0. That is racemic mixture, that is 1:1 combination of pair of enantiomers, and resolution is that if you can separate the racemic mixture into the individual enantiomers. So, resolution is separation of a racemic mixture into the individual enantiomers. Okay. Now, the next thing is very important in stereochemistry, and that is, as I said, that since the time of Van 't Hoff and Lowell, who proposed that the carbon is a tetrahedral carbon, and this tetrahedral carbon, because of this tetrahedral nature of carbon, that gives the possibility of generating another molecule if the ligands, that means the substituents attached to it are different. If the 4 ligands are different which are attached to it. Okay. So, I want to make a carbon where there are 4 different ligands. So, one is red, one is this pink, suppose this is a ligand, that means a substituent, there is a white ligand, and there is no other color. Let me see. So, I have another, suppose I put a carbon here. So, if you look at this carbon is attached to a methyl, this is one ligand, this is another group represented by white or an atom, this is an atom or a group represented by the red, and this is another substituent represented by pink. Okay. Now, this is a 3-dimensional molecule, because this is a tetrahedron. You cannot draw a tetrahedron by putting all the bonds in the same plane, because that never happens in a tetrahedron. If you inspect the tetrahedron, it has got some special features. The features is that, first of all, you cannot place more than 2 bonds in one plane. So, you have this tetrahedron, and these 2 bonds can be in one plane, but you cannot place 3 bonds into one plane. So, if these 2 bonds in a plane, then what happens to the other 2 bonds? One bond is above this plane, the other bond is below the plane. Okay. So, that is the first concept, that maximum 2 bonds can be placed in a plane. Then the other 2 bonds, one becomes above the plane, and the fourth bond becomes below the plane. You can actually place the carbon in the plane, and then what you can have, that 3 bonds are above the plane of this plane of the reference plane on which the carbon is placed, and the fourth ligand, fourth substituent is below the plane of this what I am holding. The reverse situation can also happen, that 3 bonds can be below the plane and 1 bond can be above the plane. So, these are the different possibilities. So, first of all, you cannot place more than 2 bonds in a plane, and second one, that 3 bonds can be above the plane in which the carbon is residing only, and then the fourth bond will be below that plane. Vice versa is that if the 3 bonds are below the plane, then the other bond will be above the plane. Okay. Now, the question is how to draw this 3-dimensional structure into the blackboard, which is a 2-dimensional plane. Okay. So, there are some notations that were used, that when we draw a bond, usually we draw a bond by a line. Now, in stereochemistry, a line means a bond, no doubt, but this line is in the plane of the bond, is lies in the bond lies in the plane of this board, this line. If I say a simple line, see if I draw another line, that means this line also is in the plane of the board. What happens to the other 2 bonds in a tetrahedron? As I said, if 2 bonds are forced in a plane to lie in a plane, the other 2 bonds cannot lie in that plane. One bond will be above the plane and the other bond will be below the plane, and this is suppose the carbon, which is attached to the 4 different groups. Suppose this is a group A, this is a group B, and then you have a groups D and the group E. So, one will be now above the plane. Now, how to show that to the students or to people who is observing this molecule, that how to make them aware of the fact that one bond goes above, and the way to do it is that you make it a dark bond, but you see the way it is drawn, it was first narrow and slowly the dimension becomes more, the width becomes more. That means, as you go away from the carbon, the substituent is also moving above the plane, more and more above the plane. Okay. So, this means the bond is above the plane of this board, and the other bond which will now the below the plane of this board. So, that will now be looking like this. So, this is the third substituent and this is the fourth substituent. So, this is the way you can represent a tetrahedron. This is one way, that 2 bonds in one plane. The other is that 3 bonds above the plane. So, now you know this, that when I draw this darken the bonds and show it, that means these 3 bonds are above the plane. And what did I say, that if 3 bonds are above the plane, then the fourth bond will lie below the plane. Okay. So, this is another way of representing the tetrahedron in the 2-dimensional plane. And there is a third one option I have, is that 3 bonds are below the plane and the fourth bond will now be should be above the plane. So, these are the 3 situations, and all the 3 situations can be shown in this perspective formula. Okay. This is what is called the Wedge formula, the Wedge representation of 3-dimensional molecules, that where, remember, if you have only the single normal line, that means these bonds are lying in the plane of the board. If you are drawing it in the paper, then that they lie in the plane of the paper. This is above the plane of the board, this is below the plane of the board. Okay. So, these are flying wedges. However, they are little bit hard to visualize, because you have this alpha beta concept here. Okay. Now, there are other kinds of perspective formula which are more useful in stereochemistry, in stereochemical representation of molecules, and they are called projection formula. Okay. Projection formula. What is projection formula? That means projection means, you know that projection means that if you have a line on a plane, above a plane, above a certain reference plane, and what is the projection of this line? That you draw a perpendicular from the end point to the plane, and then that means you draw a perpendicular from here to there to the plane, and then you draw the line. So, that is what is called the projection. The simple mathematical concept, that if you have a bent line, and if I see what is the, say what is the projection of this line on this plane, the projection is draw the perpendicular, and this becomes the projection of this line which is drawn here. Okay. So, based on this principle, you have different projection formula. That means, what you do, you take the 3-dimensional molecule and then you draw the projection of the molecule on the plane, and then see how does it look. What are the projections? Because what we draw is the projection that is obtained by drawing all those perpendiculars to the reference plane. Okay. So, there are 3 kinds of projection formula. The most common is the Fischer projection formula, and the most common is the Fischer projection formula, and the others are Newman projection formula and Sawhorse. Okay. So, let us first come to the Fischer projection formula. What is that? That in Fischer projection formula, you hold the molecule in such a way that, suppose I am the observer, you hold the molecule, that means the carbon containing the 4 different groups, in such a way that the bonds, that none of the bonds, I have a reference plane here, I consider a plane like this. So, none of the bonds are in the plane, only the carbon is in the plane of this paper. So, what happens now? 2 bonds, if I am looking from this side and this is my reference plane. So, what happens? 2 bonds will be towards the observer if the observer is from this side, and 2 bonds will be behind the observer. That is first thing. So, when you draw a Fischer projection formula, you view the molecule in such a way that 2 bonds are facing towards you and 2 bonds are going away from you. But not only that, there is another one restriction, and that is put in Fischer projection, is that the bonds which are towards the observer, they should be in the horizontal direction, and bonds which are away from the observer, and they should be in the vertical position. So, basically what I am saying, that you hold the molecule in such a way that it looks like, in the Wedge formula, it should look like this. So, these 2 bonds are towards the observer because they are now above the plane of this board, and the other 2 bonds will be away from the observer, but they are in the vertical line. So, if I am the observer, so that means what I see, that these 2 bonds are facing towards me. That means, if I extend my hands, one is pointing to my right hand, another is pointing to my left hand, and this D group is away from me, but it is pointing towards my head, and E group, it is also going away from me, but it is pointing towards my leg. Okay. Now, what I do? I draw projection of these bonds, of these bonds onto the plane of the board. So, when I draw the projection, that means this will go down and I get a line, simple line like this, and for the moment we keep the carbon, but in Fischer projection carbon is not shown. But so this is the projection of B, of the bond connected to this carbon. This is the projection of A, and this is the projection of D. Now, this projection has to be coming from the back side, and this also the projection has to come from the back side. So, these are the projections that you will have of all the bonds in the plane of the board. Okay. Now, you remove the carbon and it will look like a cross. So, this will be D, this will be B, this will be A, and this will be E. So, I hope this is clear. That means, if while drawing the Fischer projection formula, I should write this is the Fischer projection formula. In the Fischer projection formula, what the molecule is first held in such a way that the horizontal bonds are towards the observer and the vertical bonds are going away from the observer, and then you take a projection on the plane, the reference plane, in this case the board, and then you will see that you are forming a cross, and then you put the atoms again. So, this is the Fischer projection of this molecule. Okay. Now, the problem is always the molecule will not be drawn in this fashion. The molecule can be drawn, as I said, in various fashions in the Wedge perspective formula. So, if a molecule is drawn like this, suppose, say this is beta, this is alpha, and these two bonds are in the plane of the board, and I ask you to draw the Fischer projection formula of this. Now, this molecule, if I stand here in front of this molecule, then this is not projected according to the Fischer projection, because in Fischer projection two bonds has to be beta, and they have to be also towards the two hands in the horizontal direction, and the other two bonds should be away from the observer and also should be towards the vertical axis, but this is not drawn in such a way. So, how to now convert this into the Fischer projection? Now, there are several ways you can do it. It all depends on the visualization, that visualization concept that you have, 3-dimensional visualization, but I can give you some simpler way to solve this type of problem. So, the problem is draw the Fischer projection formula of this molecule. So, what I suggest that now one option is you rotate the molecule, you rotate it in such a way so that the two bonds, so that it looks like what is just before drawing the Fischer projection. So, you have to turn the molecule. Now, while turning the molecule you can make mistake, that is a problem, that you have to turn this, D is already up. So, you have to turn this D. So, you have to bring the E up also, then you have to make out where are the A's, where are the B's. The other option is that do not turn this molecule, keep it as whatever it is. The observer is flexible, observer is the student or the teacher or whoever is seeing this molecule. So, if the observer thinks that he is standing here in a vertical manner, he is standing here with his head up and leg down. So, he is standing at this position, head is up and leg is down, and he now sees the molecule from this direction. So, what will happen if he extends his hands on the two sides? So, these two bonds A and B are now projected towards him, because he is standing here and he is standing again, I repeat, he is not standing like this, he is standing in a perpendicular to this plane of the board, he is standing like this, his head is here, his leg is below the plane of this ring, and his left hand will be here and his right hand will be on this direction. But if he stands here, the interesting point is he is now satisfying the condition of the Fischer projection. That means, the molecule now, these A and B are towards his two hands and they are also going towards him, and what happens, this D is going away from him, E also is going away from him, but D, since it is above the plane of the board, so this is pointing towards his head and this is pointing towards his leg, but they are going away from him. So, if you now draw the Fischer projection, that means I am seeing from this direction, my head is here, I am seeing in I am sitting in an orthogonal position, standing in an orthogonal position to the plane of the board, and then I can draw the Fischer projection very easily. So, what will happen here? I see from here. So, you draw the cross again, and to the left hand, now you have to decide where is your left hand, where is your right hand. The left hand is on this side and the right hand is on this side, and where is your head? D is pointing towards your head, but it is going away from it, and that should be the case in case of Fischer projection. So, that is D and that is in. So, this is the way to draw the Fischer projection. Situation may be a little bit more complicated, that if I draw it in, say I have 3 bonds like this above the plane of the board, and the other bond must be, as I said, if 3 bonds are above the plane, then the 4th bond has to be below the plane. If that is the case, then how to draw the Fischer projection from this? Now, the simple way to do it, as I said, do not turn the molecule. Best is that you position, the observer should position himself or herself in such a way that the molecule just looks exactly what is before drawing the Fischer projection. That means, the horizontal bonds should be above the plane and the vertical bonds should be below the plane. So, where the observer should place himself or herself? So, if the observer is now observing from this side and extends his hands towards this and towards on the other side, then you can see that these 2 bonds will be towards him, D will be towards his right hand, E will be towards his left hand, this B will be towards his, this B and E are going away from him and they will be occupying the vertical axis, and B will be at the top because it is now the it is in the headward direction and this is in the direction of the leg. So, you see from there and then you draw the Fischer projection very easily. So, this will be the right hand. So, that will be D, this will be going to the left hand, that will be E, and that will be B, and that will be A. So, this is the simplest way of drawing the Fischer projection, even if it is given in different perspective ways. Wedge formula, you can easily convert, and as I said, there is no harm in rotating the molecule, but rotation can draw you into trouble. That when you rotate the molecule, you have to see where it is after rotation, how does it look. The better approach is that the observer makes room, that he stands in such a way, such a corner, that it looks like a Fischer projection formula, okay, and then draw the Fischer projection. Only thing you have to remember, where is the right hand, where is the left hand, where is your head and where is your leg, then you can draw the crisscross. Okay. Now, this Fischer projection formula has certain restrictions. Restrictions means you cannot just rotate the formula at your will. Means if you have a Fischer projection formula where there is suppose a methyl, there is a Wedge, there is a hydrogen, and there is a suppose there is a ethyl group. Okay. Now, this Fischer projection formula, if you say that I will rotate this by 90, I will rotate this whole thing by 90. So, what will happen? Methyl will come here, so rotate it by 90, and then this H will be here, H will be there, and sorry, C2H5 will be there, and this will be your H. Now, if you do a rotation by 90, you actually change the molecule. This is not the same molecule as this, because when you convert, remember this, that when you convert a 3D molecule into a 2D plane, when you write that, there are some restrictions that are imposed now. You cannot rotate it at will, but if it is in the 3-dimensional perspective formula, you can rotate it. There is no restriction of rotation. Here there is some rules that needs to be followed, What is the first rule? That you cannot rotate the Fischer projection formula by 90 degrees in plane. So, in plane, this is in plane rotation, you are keeping this whole thing in plane and rotate it by 90 degrees. That is not possible. So, what actually is interestingly, you can try that this actually is becoming the mirror image of this one, if you do this 90 degree rotation. What is allowed is 180 degree in plane rotation. In 180 degree in plane rotation. That means, this methyl is here, C2H5 is there, and then OH is here, H is here. So, 180 degree in plane rotation is allowed, 90 degree in plane rotation is not allowed. What other things are allowed or disallowed? Disallowed is 180 degree out of plane rotation, 180 degree out of plane. See, there are two ways of doing 180 degree rotation. Either you can take this and make it, you rotate it in the plane, that is one way of rotation, or you can rotate it 180 degree out of plane. That means, you take the molecule out of the plane and then again put it in the plane. So, these are the two ways. So, 180 degree out of plane rotation is not allowed. Then what is also, what are the other rules? The other rule says that you can exchange, if you exchange the position of these ligands. Suppose I exchange OH with methyl, I put OH here, methyl here, whether that is allowed or not. The rule says that exchange in a group of 3 is allowed. Exchange in a group of 3 is allowed. And one exchange is disallowed. Okay. Now, what does it mean? One exchange means this exchanging methyl with Wedge. So, if you put the Wedge here and the methyl here, that is not allowed. Okay. That changes the molecule. What does not change the molecule is exchange in a group of 3. That means, you bring the methyl here, Wedge here and H there. That is what is called exchange in a group of 3. Okay. So, that is what is allowed. One exchange is disallowed. So, that is, I think, all about the Fischer projection formula. We can come back to this issue later on when we talk about the absolute configuration of molecules. This will be extremely helpful in drawing various stereochemical molecules with various types of stereochemistry involved. Okay.